Good morning, all. Can you hear me? Hello?
Yes, we can.
Brilliant. Okay. So this is one of the foundation lectures in immunology that has got to understand where it's coming from. And there are certain aspects I want you to grasp that are not technically in the textbooks but have a correlation with our clinical work. And it's very important for us to understand phagocytosis from the point of view of its function, because I said before, that once any cell performs phagocytosis, it will do that particular function in any clinical scenario, but the target material, the target antigen will be different. In the case of tumors, it's tumor antigens. In the case of autoimmune diseases, self-antigens. In the case of microbial antigens, bacteria, microbial, and so on. But the process is the same. So that's the brilliance about immunology. All the foundation governs all the pathology that you will see in your future life. And like I said before, I predicted that then by the year 2032, there will be no official pathology. It will be immunopathology, because everything is totally based on immunology. So at the end of this, I'll give a series of small questions to do, because this will be updates. It's also good when you are also at this kind of Zoom thing. It gives me the ability to sit down and really do some serious reading in the middle of all this calamity that's going on in the campus right now. So I go through many of the things. I search for PowerPoint presentations that are simple, and I add a little flavor to it in terms of clinical, and notwithstanding, you'll also get something in terms of something to do that you need to go and do some research on, that will cement everything. So look at the cell types of phagocytosis, and we'll summarize. Nothing dramatic here. This is a bit of historical background, as you can read it. Phagos is to devour cytocell. Somebody, unfortunately, in an exam told me defined phagocytosis, and he puts cell eating. That is not exactly acceptable. The definition is very clear there. It is the process of engulfment and destruction of solid particles, for example, bacteria, dead tissue, and foreign particles by the cells. Mark you, the definition is fully encompassing and will actually be looked at when we discuss the types of macrophages that are available to us. Because right now, the current textbooks, there's not a single macrophage, but there are two types of macrophages with distinctly different roles to play. But that is the definition. Now, obviously, it is imperative to understand that it's very difficult to put short answer questions for 350 students plus. So most of the time we'll be giving you an MCQ, but that's the correct definition that you must employ. Hold on a second, I'll jump a couple of things. Yeah. So the three which are very prominent, they're neutrophils, monocytes, and macrophages. All right. And the ones which are very acutely involved in acute inflammation are neutrophils, followed by a couple of days macrophages, because they have a more robust biochemistry and physiology to withstand continued stay in peripheral tissue whilst they go about the business of phagocytosis, or destroying bacteria that the neutrophils have been actually defeated to do in a substantial manner. Okay, these steps are largely exaggerated, but it comes from acute inflammation, where we want to get our target phagocytic cells from the intravascular space to the extravascular space. And at this junction, did we cover acute inflammation? The process of the movement of white cells from the intravascular space within the blood vessels to the extravascular space. Was it covered, or did we cover it? Hello? Class rep, Madam Tracy, did we cover this? Or has it been covered?
Acute inflammation.
Yes, not just the process of getting a white cell from the intravascular to the extravascular space.
I think it was covered in first year, but we can go over it again and over.
Don't worry, if you have not done this one, this is particularly important. If you do not see it on our schedule, it is crucial that we discuss it because the process is crucial for us. If not, I'd rather do that separately. Even a different time, I don't mind. And as an extra lecture because it has severe and critical implications.
Okay.
All right. So for the time being, I'm going to speed up Kidogo, summarize, but then if you go through the thing and you feel that this needs to be done and it's not been done, especially, then we'll find a special day to do that because it has very crucial implications. Okay.
Okay.
Okay, fine. The steps we're talking about, let's talk about imagination. What is the essence of this concept of imagination, and what does it actually mean in terms of phagocytosis? This is one of the first, it is actually a condensed series of steps that allow or permit that white cell to gain access to the extravascular space. And what you're seeing there is highly what's it called, visualized pictorially, but it has got especially interesting aspects that we can be discussed as a longer lecture that will take you about 30 slides. This is actually a gross summary. Nonetheless, during normal physiological blood flow, you have what is termed as laminar flow that directs cells towards the center. At the periphery, you have fluid. And that is crucial. But when you have acute inflammation, especially when you're doing the surgical pathology, you will know that there is vasoconstriction of blood vessels and vasodilatation. This concomitant vascular dynamic situation results in turbulent flow that will make sure that the cells that are in the center come into contact with the endothelium. The endothelium is replaced by these single flat cells that you can see to which the white cells are attaching. Now, the white cells in summary here have various projections that are exhibited in times of inflammation that permit that white cell depicted with having this circular motion or rotating to the right. It has various projections you can see called little green ones that are attaching to selectins and little other ones which are plain. All these things do is that they actually bind to the endothelium, and the white cell rate of flow is reduced markedly because every successive binding results in slowing down of the white cell. So if you go to the first place where you see the yellow arrow engaging from the left, the first encounter with the endothelium has a certain binding between ligands and the various things you may see, but ultimately it comes to a rest. So the one where you see the white cell looking a bit plump is where it's actually come to a full arrest. This is actually very, very superficial. It requires a lot of other explanations because it's not only selectins that are there are things like integrins, adhesion molecules that are very crucial for us to understand that. And if that's not been done, it doesn't make a difference because this is just the prelude to phagocytosis. You can separate them into two, all right, very, very easily. So what we want to say for the time being is you want to get your white cell into a position where it will actually come into contact with endothelium and escape on the extreme right through an interendothelial space and make its way towards the site of inflammation. So what we're talking about is the white cell looks like a tennis ball that you throw down a corridor. First, it starts bouncing with high bounces, intermediate bounces, low bounces. It then rolls and comes to a rest. That's the same thing that's happening where each bounce reflects an interaction between endothelial cell binding receptors or projection that will also bind to white cells. It eventually slows down the white cell completely, and then it becomes attached. So that flattened white blood cell is one to the fourth one on the endothelium, reflects and arrested or stopped WBC. It does not move any further and now attempts to escape between the endothelial space. All this is highly dependent on a focus of inflammation that is extravascular, because wherever you're going to do some phagocytosis, etc., we are going to have a certain degree of breakdown of products or destruction of products. These are chemotactic. They attract white cells. They affect the endothelium such that it is now suitable to cause arresting of movements of white cells and their direction to the source of inflammation. So this is highly summarized, and for today's lecture, it's just to appreciate that, yes, this happens through the intermediation of things like the integrin selectin that slow down your white cell, let it attach to your endothelial surface of your blood vessel, and then escape between interendothelial spaces. And they do that along a chemotactic gradient. That's still the same thing, don't worry. Yes, for all intents and purposes, I've sent this PowerPoint to all of you to the class, so you should have it. And then with that, we will actually, you can annotate notes to that. Now, look at that process called diapedesis. That is the process in which a white cell projects or protrudes a cytoplasmic projection looking like a tongue going through under the influence of a chemotactic source. As you can see, the amount of dots in the region of the chemotactic source are has a higher number of white blue dots as opposed to the gradient, which goes all the way to the blood vessel. But still, all these white cells can home in on these signals to go into the target place where those chemotaxins are being produced. Those chemicals that attract white blood cells are called chemotaxins. As you do know, there's also, it makes things much more simpler. During acute inflammation, we have increased permeability of blood vessels, and that's also crucial. That helps the process. So this one goes along this process, and effectively the neutrophil or macrophage, the macrophage being bilobed, will reach that source. Yes, potent chemotactic substances or chemokines are leukotriene B4, C3A, C5A, and cytokines. Of which of the two complement factors has got a chemokinetic property in addition to chemokinesis? So chemotaxis, sorry. Which of the two, C3A or C5A, has, in addition to chemotaxis, a property of chemokinesis? Anybody? It is crucial because it's very, very important. By the way, it comes as an MCQ question sometimes. Anybody? From the complement system, these are A subunits that are split off and go into the extravascular system, and they form an important function. Which of the two has both functions of chemotaxis and chemokinesis? Anybody want to hazard a guess?
C5A.
Brilliant, exactly. All right. C5A has got both properties and is very crucial, by the way. Okay. So the attachment stage is when actually we have left the blood vessel that we saw in the previous thing. We have gone along the chemotactic gradient. We've reached the target source where we've engaged microbes. So one of the processes that can occur, that can help, is employing complement, okay? As you do know, these P subunits, especially C3b, are powerful opsonization chemicals, as is IgG. If you remember, we recollected IgG is one of the most important immunoglobulins because it has not only an opsonin effect, but an antitoxic effect. So if you want to bind these things through the complement, you can do it through IgG or you can do it through C3b opsonin. And by doing that, they attach to the white cells and immobilize them. All right, so how do they do that? On the white cell, there are receptors for C3b. C3b attaches itself to a microbe. So you have a microbe attached to C3b, attached by a receptor to the macrophage. You immobilize it and make life easier for phagocytosis. At the same time, you have complement. Complement will have a receptor, an FcR1 receptor, which is very rapid, FcR1 receptor that will has its own, it will bind on to a neutrophil through this receptor, at the same time engaging the microbe. So these are two ways in which you can bring about actually slowing down, literally, and immobilizing your target. Now, this is the crucial part I want you to appreciate. But before we do that, we want to engage one more way in which we can actually respond to, what do they call it? Respond to microbes in that through a function or a process of receptor recognition. So let me go there straight and say that on microbial cells, there are particular molecular patterns or patterns of biochemical molecules on the surface that a white cell can roughly recognize. And I use the word roughly and we bold it because whatever the case might be, all manner of microbes can have those particular biomolecules to which a white cell be attracted. I think like they use things, white cells use things like toll-like receptors, TOLL-like receptors. They use things known as pattern recognition receptors that they elaborate to recognize things on microbes, like things known as PAMPs and DAMPs. For your homework, you will find out what is a PAMP, not a PAMPA, but a PAMP and a DAMP, and how it correlates with PRRs. I will repeat, for the purposes of extra reading, you will find out the elaboration of the meaning of PAMP, PAMP, and DAMP, degraded. They are products of degradation from microbes, DMPs, PMPs, and pattern recognition receptors on macrophages. When these two interact, the macrophage will home in because it recognizes these receptors on the microbe and eventually undergo a process by which the cytoplasm of the phagocyte forms a cup-like structure by actually extending little feet called pseudopodia, false feet, that form an indentation by contracting or extending around the so-called purple or antigen microbe that has got all these opsins, etc. So it undergoes a process of endocytosis, making a cup-like structure from the plasma membrane that goes into the cell by the two opposing lips. You can see the little finger-like projections, progressively extending and eventually meeting the two arrows in the middle. That we call endocytosis, the formation of a vacuole-like structure from the meeting of two opposing pseudopodia, which are cytoplasmic projections of the entire cell that meet in the center and engulf that with a bit of fluid. All right. So from B, as we've just done, we have the formation of a phagosome. That is the cytoplasmic vacuole that contains the offending microbe, the offending tumor cell, offending whatever it might be, whatever target you have, has to be enclosed in a intracellular cytosolic organelle known as a phagosome. This requires energy, obviously. At this stage, we go out from B, C, we're now at letter D. We have these little tiny little brownish little packets of enzymes known as lysosomes that fuse with the membrane of the phagosome to form a phagolysosome and commence the destruction of the contents or the target or the offending agent, the antigen. Now, what is the essence of doing this and why should we worry about collisions? There are certain bacteria like TB and Listeria monocytogenes that prevent phagolysosome function by causing acidification. They acidify the contents of that phagolysosome, rendering it useless because the enzyme that you require a pH that is alkaline, a raised pH. And that is how they escape the immune systems. So when we were doing things like antigen presentation, we shall be locked into understanding this process because it also involves TB and Listeria, and we'll discuss that. We talk about so-called antigens that are from the extracellular space and those found in the intercellular space. Again, at this stage, it is energy utilization is maximum because this is a process that requires enzymatic things, enzymatic processes. That's okay. Good. So above you see a process, but actually when we talk about degradation or destruction of the target material by the lysosomes, those are vacuoles filled with lytic or lytic enzyme that destroy the target. There's oxygen dependent and oxygen independent. Now, when you ever had a scratch or a cut, etc., and it has become infected, what did you feel like? Besides pain. This is crucial because we've got to correlate what we're doing today with what we're going to see clinically. Remember in my class, venture a guess, you look stupid for 3 minutes, or nowadays, thanks to Zoom, you sound stupid, but we can't see your face, obviously, which is fortunate. But to remain silent is to remain uninformed or misinformed. So when you've had a cut that's developed a bit of infection, how does it feel? Or that area in particular?
It feels hot.
It feels hot, isn't it? It's painful, hot, discomfort. The actual heat that you're experiencing is actually the phagocytic process in the oxygen-dependent phase, where we're going to break down ATP to produce energy to produce certain results. And therefore, if you have a wound that is cold and still infected, it smells, you should worry you because it will actually indirectly inform you that you have no phagocytic activity in that region. If you see a wound by Clostridium tetanus, which you'll actually see, and I hope to God you never see it clinically because it's very dramatic, the wound is very cold, and does not even wounds due to TB, they're not hot, they don't exhibit any kind of heat because there's no phagocytic process undergoing that. Formally, when it becomes infected, what is the color of that wound? If you look at that wound, besides it being cut, etc., what is the color of an infected wound? Is it red, green, yellow, blue?
Red.
Yeah, only red. You don't ever see when it's red, it becomes yellowish. Have you seen that in a wound? It's yellow.
Yellow.
With yellow, thick sometimes. When you go to the wards, when you appreciate what you're looking at that particular time is dead neutrophils. They die in mass, and since they're highly destroying proteinaceous material, they form this yellowish kind of discharge due to the production of PMNs. Because once neutrophils form the function of phagocytosis, they actually die. So with that plus the cellular debris, they form this yellow, sometimes greenish, depending on what kind of bacteria it is, discharge. Okay. So what you're seeing today, phagocytosis, is clinically being done as you see it in injury, especially cuts, wounds, etc. So the oxygen-dependent bacterial cytal mechanisms are mediated by oxidizing agents, which we'll mention them, while the independent works on lysosome enzymes. So there's a two-pronged attack, or two-armed attack against the target. You can either use enzyme directly from the lysosomes, or you can use the neutrophils biochemical apparatus to bring about oxidizing agents. All right. Now, whenever you've had a wound at home, how have you treated it, or has it been dressed by your mother, maybe your brother, your father, or somebody? Maybe you've gone to the doctor. What does he do when he actually dresses your wound, especially if it is infected? Come on, guys. Most of you must have injured somewhere, got cut or something. How did your mom know dress? Sorry? Used?
Use of hydrogen peroxide.
Brilliant. Anything else? You ever seen betadine at home, or iodine solution around?
Yeah.
You've seen that, huh? Yeah. Yeah, exactly. Well done. Now, we're going to explain the rationale. What you're actually doing is doing the phagocytic process in vitro. Let's see how. Leave that here. In the body, in the biochemical systems, what cycle produces ATP? Biochemistry, what cycle produces ATP?
Krebs cycle and glycolysis.
Glycolysis, brilliant, okay? So we're generating energy through ATP, so? And which other cycle within the biochemistry that you've been taught generates reducing power?
The HMP shunt.
Huh?
Pentose phosphate. Hexose monophosphate.
Okay, so what is a very powerful reducing agent that you know as that works in those that cycle?
NADPH.
NADPH, yes. NADPH, NADPH2. So if you take oxygen, O2 oxygen, and you reduce it using the hydrogen from the NADPH2, you'll produce reactive oxygen radicals like O minus, O2 minus, and O3 minus. At the same time, you can break down water or chloride from H2O into OH minus. At the same time, you can reduce chlorine to chloride, bromine to bromide, iodine to iodide. All of these negatively charged reactive species attack cell membranes of microbes. All right? And therefore, there's a lot of energy consumed at this particular stage. Equally, we also have Na2. When you break down citrulline from arginine, the two amino acids, you get an NH2 group, which you can actually hydrolyze reduce and get NO minus, NO2 minus, and NO3 minus. This is very crucial because certain microbes actually evade the immune system by blocking these pathways and knocking out the NH2, NO2 minus pathway. Ultimately, whatever happens, all of these will digest the thing through enzymatic action or the production of radicals that destroy bonds in the cell membrane of microbes. They destroy bonds in the gram-negative and gram-positive and gram-negative bacteria. They have lipotecoic, they've got these gram-negative cell walls that have susceptible bonds to reactive species. Sometimes you can call them reactive oxygen if you come from oxygen, etc. But they actually called radicals, reactive or reactive radical, just radical production through to reduction by NADPH2. Ultimately, the destruction results in accumulation of the debris, the destruction, that you can see in the little particulate purple tissue, which have to be extruded. What does it really mean? If you go to F approaches the cell membrane, the reverse process of endocytosis occurs, and we call it exocytosis. So what you did in endocytosis, you formed a cup. This you contract behind the two lips, contract behind the vacuole, and extrude the rest of the stuff outwards. That stuff is what is going to cause the chemotaxis and the chemokinesis in C5a and attract this thing. The destruction of your microbes produces dams. Dams also attract or form a trigger for recognition by macrophages and neutrophils. Now, next thing you have to do is you need to make a list of bacteria and, microbes that resist the phagocytic process. I repeat, make a list of microbes that resist the phagocytic process and exactly what particular step they interfere with. Is that okay? Because often I will ask you the following bacteria evade phagocytosis by, that would be an MCQ question. If you do it in microbiology, I'll be asking you to say, write short notes on how bacteria evade the phagocytic process. So I repeat, an MCQ can ask you which microbes evade the phagocytic process, or I can ask you write short notes on giving examples of microbes that evade the phagocytic process. Is that okay? Hello?
Yes.
Yes, so that will be the thing, do that. And that's where I will set questions from, definitely. I don't want to play games. Life is short. We are having a COVID system going on that's depressing and stressing everybody. So I don't want to make your life unnecessarily unhappy or misfortunate. There's enough misfortune going on. I've had enough of it. I've had 2 cousins with COVID. I had my only sibling who goes COVID in HDU. She's come out. Her husband was in HDU too. It was just like a mess. I'm just praying, God, that this thing can end and we can get back to some degree of normalcy. Driving people insane, I tell you. So that's why I'm stuck at home over 58, looking quite rustic. But don't worry, if there's any hope, I wish you to wish me the best, because I'm starting adult literacy classes in IT as of tomorrow for the next 2 months. So I will hopefully be in a better position to use this equipment known as a laptop. Can I have a warm send-off at least, or some degree of appreciation? Sir.
All the best, sir.
I'm telling you the way I'm so badly off, it's embarrassing, I tell you. So take care. Look after yourselves. Yeah.